There are many terms and types of qubits to consider when piecing together these QPUs in a network for a data center. So you'll hear me throughout the talk kind of touch on these different qubit types. So I wanted to start with a common vocabulary and taxonomy of these kinds of qubits. So at the end of the day, when we think about quantum computing and the algorithms and the applications of a quantum data center, we like to talk about logical qubits. Logical qubits are essentially the error-corrected qubits and quantum states that are ideal, right? They're not prone to errors. They are usually encoded in a series of physical qubits. These are the actual qubits on the device, whether it's superconducting, trapped ion, cold atom. But we like to code and program these quantum computers at the highest level with logical qubits that we can actually do, some quantum advantage and really kind of take advantage of the logical qubit level. Now, within physical qubits, there are different kinds of qubits that may be on the chip or in the ion trap or cold atom, where you'll have different kind of roles for these physical qubits, depending on the architecture, depending on the company we're talking about. But generally, you'll see these kinds of physical qubits appear in the architecture, and they're used in different ways. So at the top, we have computational qubits. So these are the qubits inside the QPU that are actually running the gates and the algorithms and the computational instructions on the chip or in the trap. We have ancilla qubits. These are essentially extra physical qubits that we use for redundancy. So similar to how in today's classical systems like CPUs and GPUs, there's a lot of error correction and redundancy built in that we kind of take for granted. And the similar analog applies to quantum computing, where we have these redundant ancilla qubits that are used for error correction. So they encode a logical qubit, right? This abstract kind of quantum state into an array or a series of ancilla qubits around it. Now, we have also storage qubits on some platforms. So even within a single QPU, you may have different regions or zones of the quantum processing unit that these physical qubits are perhaps better at storing quantum states for longer time. So they sometimes can have longer coherence, better isolation from the rest of the chip, lower crosstalk. So we're starting to piece these kinds of qubits together, similar to how today's computers or systems on a chip work, where you have different roles of bits, right? And you have storage, you have RAM, you have processing, all with different trade-offs and properties. Now, as we move to the right of this slide, we get more into the networking side of things. So to realize this vision of a quantum data center, each QPU will need to have some set of communication qubits. So these are stationary interfaces, or quantum interconnects, they're sometimes called. And the whole idea here is that these physical qubits on the QPU or adjacent to the QPU are responsible for interacting with the flying qubits for the network. So we have stationary qubits and flying qubits. Flying qubits are photonic, so they're optical signals and they're pulses of light. So these communication qubits on the QPU are really interfacing with the network, and they're responsible for generating entanglement with the stationary qubits and the rest of the QPU. So this is a really important interface. There's many different approaches to building these quantum interconnects, and they are somewhat modality specific. So creating an array of communication qubits or network interfaces, quantum interconnects for superconducting will look widely different than, say, for a trapped ion system. Finally, even within the flying qubits and the photonic regime, where we're talking about networking and sending qubits around between different processors, there are also different ways to encode our qubits, our quantum states, in light. So there are different photonic kind of degrees of freedom or dimensions we can leverage to encode our quantum state. So we can use for example, the property of time. So the arrival times of these photons to encode our quantum state based on like early arrival or late arrival. We have polarization, essentially the kind of spin of the light. We have frequency as well as another degree of freedom we can encode quantum states in. And we also have spatial encoding, where light can take different paths as they pass through optical components, say like beam splitters that can split up your beam of light into different paths. So different ways we can encode these flying qubits as well. So hopefully this is a useful common vocabulary, but also I think it outlines the complexity of these different qubit types and abstraction levels, some of which are very much tied to the QPU platform. Others are more tied to the network. Others kind of sit in between. Others are used for higher level kind of computational descriptions, et cetera. So there's a wide array of qubit types, and they all play a critical role. So the future quantum data center will have, most, if not all, of these qubit types.